Welcome back to Science Modernizers. Welcome back to this video. In today's video, we are going to be talking about the photoelectric effect. And what are the objectives of the video? The first is we should be able to define photoelectric effect and know the Einstein's explanation of photoelectric effect and the equations involved. And lastly, we are going to see questions. So let's get started with the video. So we are going to begin with the definition of photoelectric effect. What is photoelectric effect? The photoelectric effect is a phenomenon where electrons are emitted from the metal surface when light of sufficient frequency is incident upon it. So if you have a metal surface, say of this nature, this metal is made up of electrons which are in their ground state. Now for them to be excited, we need a source of energy, and this source of energy is from a given source which we can call S. That's our light source. This light can be light of any color, it can be infrared, UV, etc., and has a given frequency F. So these light rays which are falling have sparks of energies which are known as photons or quantas. So this energy gives or transfers energy to the electrons which excite them, and either they are going to be excited and skip from and be ejected from the surface of the metal or not. So if they are ejected from the surface of the metal, then photoelectric effect has occurred. So we are going to see the conditions for photoelectricity to occur on the surface of a given metal. Now let's see the Einstein's explanation of photoelectric effect. Einstein resolved this particular problem using the Planck's revolutionary idea that light was a particle. Now in wave-particle duality, we are going to see that while light behaves both as a particle and as a wave. Now the energy carried by each particle of light, called the quanta or photon, is dependent on the light frequency as shown by the equation which you are going to see below, that is E is equal to hf, where h here is the Planck's constant, f is the frequency of the radiation, and E is the energy. So the Planck's constant has a value of 6.62 times 10 to the negative 34 joules second. So since light is bundled up in photons, Einstein theorized that when a photon falls on the surface of the metal, the entire photon's energy is transferred to the electron. Now let me explain this a little bit diagrammatically. Now this is what we see. If you have a surface of a metal and we have a source S which gives energy to that surface. Now every metal is categorized with a particular property, and every metal has what we call the work function W0 or phi. Now the energy which is for photoelectric effect to occur, the energy which is supplied by this source should overcome the work function of this metal, which is the minimal energy required for electrons to be ejected. And when electrons are ejected, so I have the energy from the source. From the law of conservation of energy, we can write an equation. This should be equal to the energy required to overcome the work function, and the work function is the minimal energy which is required for electrons to be ejected from the surface of this metal. And then when the electrons are ejected, they now move with a certain speed and they gain kinetic energy plus a half mv squared. Now we are going to see that this kinetic energy, when we have a maximum kinetic energy, that's the Ke max, the maximum kinetic energy will be equivalent to the stopping potential. So that's how that process occurs. So there are very simple equations to get. Okay. Now, a part of this energy is used to remove electrons from the metal atom and the metal atom's gas, and the rest is given to the ejected electron as kinetic energy. At threshold frequency F0, electrons are just ejected and do not have any kinetic energy. Below this frequency, there is no electron emission. Thus, the energy from the photon, or the energy of the photon with this frequency, must be the work function of the metal. So what then is the threshold frequency? We are going to see the definitions in the next slide. but it is the smallest frequency which is required, or the threshold frequency is the smallest frequency which is required for photoelectrons to be ejected from the surface of a metal. Now let us see this mathematically, as I just wrote on ink. So it means that if the energy of a photon, if the energy has just attained only the work function, that is, it is just at a state where electrons are just being ejected without them actually gaining enough kinetic energy for their movement, then that energy will be equal to the work function. And the work function W naught is equal to phi, which is equal to HF naught. And so from there, we can also deduce the maximum kinetic energy. And as I said, as the energy strikes the surface of the metal, it is that energy has to overcome the work function, and then the work function plus the amount of kinetic energy which the electrons will gain, which is known as Ke max. And so we have that the maximum kinetic energy will be given by HF minus HF naught. So as we saw that E was equal to W naught plus Ke max. So from here, making Ke max the subject, we have Ke max to be equal to E minus W naught. But what's the energy? This is the energy of the incident source of light, which is given by HF minus HF naught, since HF naught is the work function. So this gives, we can factor out the H into F minus F naught. So this is the maximum kinetic energy as shown here. Okay. Okay. So from there, the kinetic energy maximum is the maximum kinetic energy of the electrons, and it is calculated experimentally using the stopping potential. The stopping potential EVS is equal to a half mv max squared. Thus, Einstein explained the photoelectric effect by using the particle nature of light. Okay. Now let's get the definitions of some basic terms in photoelectricity. The first is the threshold frequency. What is threshold frequency? Threshold frequency is defined as the minimum frequency that is required for the radiation such that photoelectric effect is produced or occurs. Next, what is the work function of a metal? Every metal normally has its work function. So the work function of a metal is a value attributed to every metal. Now the work function is the minimum amount of energy required to induce photoemission of electrons from a metal surface, and the value depends on the metal. Next, what is the stopping potential? The stopping potential is the minimum negative voltage applied to the anode to stop photocurrent. The maximum kinetic energy of electrons is equal to the stopping potential, and it is measured in electron volts. What are the conditions for photoelectric effects to occur? The first condition is that the frequency of the incident radiation should be greater than the threshold frequency. That is, F should be greater than or equal to, sorry, this sign is greater than or equal to. So F should be greater than or equal to F naught. Now, the next is the wavelength of the incident radiation should be smaller than the threshold wavelength. That is, lambda should be less than or equal to lambda naught. And in terms of energy, the energy of the radiation should be greater than the work function of that metal for photoelectric effect to occur. Okay, so these are the conditions for photoelectric effects to occur. And so we are going to pass in a series of questions and see how to solve some basic problems on photoelectric effect. And if you have any problem which you can propose, you propose the problem, but don't forget this sign is greater than or equal to. Okay, now we have problems. The first question: show that the photons in a 1240 nanometer infrared light beam have energies of 1.0 electron volts? Question number 2. To break a chemical bond in the molecules of human skin and thus cause sunburn, a photon energy of about 3.5 electron volts is required. To what wavelength does this correspond? Next question. A certain wavelength, a certain lamp radiates 20 watts of yellow light where the wavelength is 589 nanometers. How many photons of this yellow light are emitted from the lamp each second? Number 4. Determine the maximum kinetic energy of photoelectrons ejected from a potassium surface by ultraviolet radiation of wavelength 200 nanometers. What retarding potential difference is required to stop the emission of electrons? The photoelectric threshold wavelength of potassium is 440 nanometers. So let's go to the next slide and solve these problems. Okay, so let's begin with the first question. To show that the photons in a 1240 infrared light beam have energies of 1.0 electron volts. So we are going to, in order for us to prove this, we are going to use E is equal to HF, but we also know that C is equal to F lambda, from where F is equal to lambda divided by C. So this implies that E will be equal to hc divided by lambda, where c there is the speed of light, h is the Planck's constant. So let's do the numerical application. The Planck's constant is a constant which is 6.62 times 10 to the negative 19 times the speed of light, times 10 to the negative 34 times the speed of light, which is 3 times 10 raised to the power 8 meters per second, divided by the wavelength lambda, which is 1240 nanometers, which is times 10 to the negative 9. So this will give us a value of 6.62 times 10. Okay, so this gives 1.6 times 10 to the negative 19 joules. But remember, our answer is in electron volts, and the conventional factor is 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So it means that our energy in electron volts will be our energy in joules. That's 1.6 times 10 to the negative 19 divided by 1.6 times 10 to the negative 19 in electron volts. That will give us 1.00 electron volts as required. So 1 electron volt has a conversion factor. 1 electron volt is 1.6 times 10 to the negative 19 joules. So you clearly see that this is equivalent to this. So it means that that energy is simply 1.00 electron volts. And we have shown that the light beam have energies of 1.00 electron volts. Okay, let's pass to the next question. Question number 2. To break chemical bond in the molecules of human skin and thus sunburn, a photon of energy of about 3.5 electron volts is required. To what wavelength does this correspond? So as we saw in the first question, E is equal to hc divided by lambda. So this implies that lambda is equal to Hc divided by E. So this will be equal to numerical application will give us 6.62 times 10 to the negative 34, then times 3 times 10 to the power 8 meters per second. All of this divided by the energy, 3.5 electron volts, but we have to leave our answer SI unit, that is, we have to convert in joules, and the conversion factor is joules, is we multiply by 1.6 times 10 to the negative 19 joules. So if you are leaving from joules to electron volts, you divide by this. If you are leaving from electron volts to joules, we multiply. So we are going to punch that 10 raised to the negative 34 times 3 times. Okay, so it gives us, this gives 9.08 times 10 to the negative 7 meters, which is about 908 nanometers. So that's the wavelength. Let's go to the next question. Okay, a certain lamp radiates 20 watts of yellow light where lambda is 589 nanometers. How many photons of yellow light are emitted from the lamp each second? So the first thing we have to do is to calculate the energy given out by the yellow light. So that energy is simply HF, but since we have the wavelength, we use Hc divided by lambda. So Hc divided by lambda will give us 6.62 times 10 to the minus 34 times 3 times 10 raised to the power 8. All of this divided by lambda, 589 nano times 10 to the negative 9. And so we'll do the numerical application. So the numerical application gives 3.37, 3.371, 3.372 times 10 to the negative 19 joules. Now, if you want to calculate the energy per second, it means that every second, which is equivalent to a certain power radiated, will be equal to 3.372 times 10 to the negative 19 watts. And so the number of photoelectrons N that will be emitted will be the power given, that the power radiated by the lamp, 20 divided by the energy of the photons. So that's 3.372 times 10 to the negative 19. And if we do the application, we have 20 divided by what we had. So we have 5.93 times 10 to the power 19 electrons or photons. So that's the number of photons that are emitted. Okay, so for the last question, we are going to determine the maximum kinetic energy of photoelectrons ejected from the potassium surface by ultraviolet radiation of wavelength 200 nanometers. What retarding potential difference is required to stop the emission of electrons? The photoelectric threshold wavelength of potassium is 400 nanometers. So we have the threshold wavelength of potassium to be 440 nanometers, and we have the wavelength of the incident radiation to be 200 nanometers. Now, as explained earlier in the video, that's the source. in which we can illuminate a metal surface. So this radiation falls and we have electrons. So if this is of sufficient frequency f, which is greater than the threshold frequency, then the energy from the source E will be equal to the energy to overcome the work function plus the maximum kinetic energy. Now this implies that the Ke max will be equal to E, which is the energy of the incident radiation, and it is given by HF, minus the work function, which is HF0. Now this is equal to H into F minus F0. But remember, what was given to us are wavelengths. So it means H into C on lambda minus C divided by lambda 0. And this is the same as HC into 1 on lambda minus 1 on lambda 0. So if we do the numerical application, this will imply that our Ke max will be equal to H is 6.62. Let me use more space. I will create some space here. So here we have is equal to HC into 1 on lambda minus 1 on lambda 0. So clean this. Okay, so this implies that our maximum kinetic energy, that's a numerical application, will be 6.62 times 10 to the negative 34 times the speed of light, which is 3 times 10 raised to the power 8, factor of 1 on 200 times 10 to the negative 9 minus 1 on 440 times 10 to the negative 9. So if we do the numerical application, the maximum kinetic energy will give 3 point sorry, I already computed everything. Yes, the maximum kinetic energy will give 3.39 times 10 to the negative 19 already. So you have 3.39 electron volts if you punch. This value gives exactly so this value of the energy gives us exactly, sorry, while I was punching already converted. So the value of this energy gives us exactly 5.42 times 10 to the negative 19 joules. So we can convert that to electron volts by dividing by 1.6 times 10 to the negative 19. And when that is done, take 5.42 divided by 1.6 will give you 3.39, approximately 3.39. So we have about 3.39 electron volts. So that's the maximum kinetic energy. So we have the maximum kinetic energy, and now we have to calculate the retarding or stopping potential. Now we saw that EVS is equal to the maximum kinetic energy. Now this implies that my stopping potential will be Ke max divided by E, and this means that Vs, Ke max is 3.39 EV divided by the electronic charge. So the E's will simplify, and therefore we get that our stopping potential is simply 3.39 volts. That's the result. Okay, and this brings us to the end of this video. If you have any question, you can drop your questions on the comment section and it shall be attended to. And thank you very much for watching the video. Please do not forget to like, share and subscribe. Thank you for watching.